Hello everyone, I am Professor Lee from the Communication Engineering Teaching and Research section at Wuzhou University. Welcome you to this mini lecture. Today we will cover Chapter 2, Section 5, Signal Decomposition. In this session, we will study 5 types of signal decomposition. Decomposition into direct current DC and alternating current AC components. Decomposition into the sum of odd and even components. Decomposition into real and imaginary parts. Decomposition of continuous time signals into linear combinations of impulse functions. Decomposition of discrete sequences into linear combinations of pulse sequences. First, let's introduce DC and AC components. A continuous time signal can be decomposed into the sum of its DC component and its AC component. As shown in the formula in the figure, the DC component f sub dc of t represents the average value of the signal, calculated as the area of the signal over the interval a to be divided by the interval length d minus a. In other words, it is obtained via integration. In the plot, it is represented by a red horizontal line. The AC component, f sub AC of t, represents the part of the signal that varies with time. In the plot, it is shown as a blue curve. The discrete time counterpart is expressed as shown in the formula in the figure. A discrete time signal f of k can likewise be decomposed into a DC component and an AC component. The DC component represents the average value of the signal sequence, computed as the sum of the values from n1 to n2 divided by the total number of samples n2 minus n1 plus 1. That is obtained by summation. The AC component represents a portion of the sequence that varies over the index k. In the plot, the black curve represents the total signal, visually showing the composition of its DC and AC components. A continuous time signal can be expressed as the sum of its odd and even components. The even component is the average of the signal at positive and negative times. The odd component is half the difference between the signal at positive and negative times. Discrete time signals likewise have even and odd components. In short, whether continuous time or discrete time, any signal can be decomposed into the sum of its odd and even components. These two components reflect the signal symmetry and anti-symmetry with respect to time reversal. Consider example 1. The odd and even components can be sketched directly using the definitions just covered. In the presentation slides, plots of f of t, f of minus t, the odd component fo of t, and even component fe of t are shown, providing an intuitive comparison of their individual shape and their relationship to each other. The odd component fo of t is half the difference between f of t and its time reverse form f of minus t, representing the asymmetric portion of the function. The even component fe of t is half the sum of f of t and f of minus t, representing the symmetric portion. These waveform plots clearly illustrate how the odd and even components combine to form the original function f of t. A complex valued signal f of t can be decomposed into its real part and imaginary part, as shown in the figure. Before computing the real and imaginary parts, we first form the complex conjugate f conjugate of t of the signal. Using the complex signal and its conjugate, we can calculate its real and imaginary parts. A discrete time complex sequence can likewise be decomposed into real and imaginary parts. The computation formulas are the same as in the continuous time case. The real and imaginary parts together describe the complex nature of the signal. These decomposition methods help achieve a deeper understanding of the composition and structure of signals in signal processing and analysis. We can regard all continuous time signals as belonging to a single class, represented using delta signals, so that analyzing any signal reduces to analyzing delta signals. Representing complex signals in terms of basic signals facilitates their analysis and processing. Looking at this plot, We recall from calculus that a signal's outline can be approximated by infinitely many small steps, whose width delta approaches zero. The signal of this rectangular change using the step signals we studied earlier. Now, let's interpret the following formula. A continuous time signal can be decomposed into a linear combination of impulse functions, as shown in the formula below. Here, u of t is a unit step function, and delta is the time interval. This formula means that the continuous time signal f of t can be approximated as a superposition of a series of impulse functions, each located at the instant k times delta and having an amplitude of f of k, delta. Each impulse function can be represented as the difference of two unit step functions, indicating an instantaneous jump at t equals k delta. In summary, a continuous time signal can be approximated by a linear combination of impulse functions, an important concept in signal processing. After analysis, we obtain the general expression. Any continuous signal can be expressed as a linear combination of impulse functions, with different signals having different coefficients. From the signal decomposition, the signal f of t is expressed as a series of impulse functions, each having an amplitude of f of k delta and located at t minus k delta t. These impulse functions are represented as the difference of unit step functions u of t, where u of t denotes the unit step function, indicating the presence of an impulse at t equals k delta, in the limiting case as delta approaches zero. These impulses become ideal delta functions, delta of t minus tau, and f of t equals the integral from minus infinity to infinity of f of tau times delta t minus tau d tau, meaning that a signal is the integral of its impulse response. The physical meaning is that any signal can be decomposed into a linear combination of impulse functions, with different signals having different coefficients. In practical applications, when determining the response of signal f of t passing through a linear time-invariant LTI system, it is sufficient to first obtain the system's response to an impulse function. Then, by applying the properties of the LTI system, the response to any arbitrary input signal f of t can be derived. Similarly, discrete time signals also have this property. Any discrete time signal can be expressed as a linear combination of shifted impulse sequences, with different signals having different weighting coefficients. In the formula, delta of k is the unit impulse sequence. Physically, any discrete sequence can be viewed as the sum over n of unit impulse sequences delta of k minus n, each shifted by n and weighted by f of n. In the plot, the entire discrete sequence f of k is represented by impulses at various positions, each with a weight equal to the sequence value f of k. This decomposition method aids in understanding the structure of discrete signals and in analyzing their properties. Finally, please reflect on this lesson and complete the following problems as homework, with the aim of consolidating the knowledge points learned today and further deepening your understanding. That concludes this mini lecture. See you in the next class.